Okay, now we'll be discussing chemical energetics. For chemical energetics, we have energy level diagrams, and there are two of them. So this is what the diagram's axis looks like, and we have the y-axis, which is energy, and the x-axis is the progress of reaction, or basically the idea of time. As time progresses, the reaction also progresses. That is what the x-axis represents. So the first diagram we'll be discussing is the exothermic reaction diagram, where the products are at a lower energy level than the reactants. And the shape of the graph is like this. So what we see over here is that for the core content, you only have delta H identification on the graph. So this value, which is the distance in the y-axis distance between the reactants and the products, is the energy difference, right? So we call that energy difference or the enthalpy change as delta H. The triangle over there is delta, which is nothing but change in energy. For the extended course, we have this quantity over here as well. Um, so this quantity is known as the activation energy, which is the energy between, which is basically this over here, from the bump to the reaction to the reactant energy level, and we label this as EA. The second one is the endothermic, which has the same axis labels, but the products are at a higher energy level than the reactants. So the graph will be similar again, but the labeling of delta H and EA will be different. So yeah, again, delta H is the is the energy level difference between P and R, and so that's going to be delta H. And in this case, activation energy is going to be this whole thing over here. Now, one way in which we can modify this graph is to distinguish the arrows between delta H for delta H. So I'm going to write it again. If you look at this one, the reactants are at a higher energy level than the products. So the energy change is actually downwards. So we can write it as this. This can be written as the delta H. And in this case, the delta H is going upwards. So we can write it as an arrow pointing upwards. So that is one difference we can make to better our graphs. So delta H is negative over here. This is what we see in the first diagram. And in the second diagram, we see that delta H is increasing, so it's positive. So what is enthalpy, right? Well, there are some formulas for this, and the formula that is in the syllabus copy is this, that energy taken in minus energy released. But what is energy taken in for? Energy is absorbed to break the bonds, and energy is released from bond forming. Now, as a tip, we can simply use this formula over here, which is what I used as a IGCSE student, which is that delta H is equal to bond energies of the reactants minus the bond energies of the products. That is simply what delta H is equal to in terms of bond energies. Reactants minus products. Okay, so this is just a small summary in which we discuss endothermic and exothermic. Endothermic reactions take in energy to break bonds, and they take in more energy to break bonds than they release from bond forming, and thus they have an overall input of energy. So if you look at the previous slide, we just see that enthalpy change is energy taken in minus energy released. So for an endothermic reaction, energy taken in is greater than the energy output, which means that it has a delta H which is positive. So for endothermic reactions, delta H is greater than 0. For an exothermic reaction, the exit or the release of energy, that is what they do, and they absorb in less energy to break bonds than they release from bond forming. And that can be written as the energy output is greater than energy input. And therefore, using the same formula before, which is energy input minus energy taken in minus energy released. In this case, energy released is greater than energy taken in. So exothermic reactions will have a delta H, which is negative. And this is just reiterating that fact that energy is released by bond forming. So exothermic involves more bond making, and energy is absorbed for bond breaking, which means that endothermic involves more bond breaking. And activation energy, which is nothing but EA, is the minimum energy level that is needed for the reaction to begin. and for the bonds to start breaking and for the bonds to start forming. And this idea over here that delta H is positive for endothermic and delta H is negative for exothermic is what I was just discussing over here. For this reaction, the graph number one, the products are at a lower energy level than the reactants, which means that this is an exothermic reaction, and that is why the arrow is pointing downwards, because delta H is negative. For the second graph over here, this is an endothermic reaction where the delta H is pointing upwards, meaning that it is a positive value for endothermic. That is the simple fact over there. Now, systems and surroundings, they are two different entities in chemistry. So let's take a neutralization reaction, for example. In this neutralization reaction, we have sodium reacting with hydrochloric acid to give us sodium chloride and hydrogen. And in this instance, the system is basically the atoms involved in the reaction. So the bond breaking of the hydrogen chloride covalent bonds, hydrochloric acid covalent bonds, will be the system. And the bond formation of the sodium chloride ionic bond and the hydrogen covalent bond, this is what they react. These are the systems of in this reaction basically. Next is the surroundings, which is basically everything else. So this reaction could be taking place in a trough, and that trough would be what we call the surrounding. And the thing is that we cannot measure any characteristics such as temperature or the energy of the system. So we have to do instead is rely on the change in the temperature of the surroundings. So for exothermic and endothermic reactions, for endothermic reactions, they have a delta H which is positive, greater than zero. This is because they have products at a higher energy level than the reactants, and thus using the delta H formula, we obtain a positive value. Endothermic reactions are those where the energy transfers from the surroundings to the system. As we cannot measure any properties of the system, we rely on the decrease in the temperature of the surroundings to recognize the reaction as endothermic. So if we were to define an endothermic reaction, we have to say that endothermic reactions are those where energy is taken in from the surroundings to the system, and they have a delta H which is positive, or an enthalpy change which is positive. For exothermic reactions, if you were to define exothermic reactions, that would be that the energy transfer in an exothermic reaction is from the system to the surroundings, and so there's a temperature increase in these surroundings, and they have a delta H value which is negative, and you can even add the fact that they have products at a lower energy level than the reactants. That's the main definition for exothermic and endothermic, and the details that you add depend on the number of marks. So over here, complete the energy level diagram for this reaction, and we are told that this reaction is exothermic. So if it's exothermic, that means that there is an exit of heat, and so the products are at a lower energy level than the reactants. So what we can do to start off is just draw a line over here, which is for the product, which is over here, SF4 in its gaseous state. So we simply draw the graph like this, right? Now this is a 3 marker, so this is one thing. It also says that to include the arrow which clearly shows the energy change during the reaction. So the reaction is progressing like this. I'm just going to add them. And the next thing we need to do is delta H, which we already know is the distance between this. And we already discussed that this is an exothermic reaction, so the energy change is going to be negative. So what I'm going to do is make an arrow pointing downwards. And then we have the activation energy as well. So this distance from the bump to the energy level of the reactants is the activation energy, and that will get you 3 marks. Next, during the reaction, the amount of energy given out is 780 kilojoules per mole. The FF, fluorine single bond energy, is 160 kilojoules per mole, and we need to use this energy to find out the bond energy of one SF bond in SF4. So if you look at this over here, the sulfur has no bonds. So when you're writing it in our equation, there is no bond energy. There is no bond energy for sulfur, and so there's no energy taken in to break the sulfur bonds because there is no bond between them, right? So if you were to write this as an equation, it will be the F bond energy is 160. So there'll be 2 of them because there is 2 of FF bonds. So 2 into 160. That is the energy of the reactants, bond energy of the reactants. From this, we subtract the bond energy of the products, which we don't know. So I'm just going to write let SF bond energy be equal to x. So this is going to be 4 of those because there are 4 lines, so 4 bonds. So this is going to be minus 4x is equal to 780. But the fact is that this is energy given out, and that means that delta H is negative, which is why I will write a negative over here. So we just simplify this. So we get minus 4x is equal to minus 780 minus 320, and then x is equal to 780 minus 780 minus 320 divided by minus 4. So that will be your answer, which will just plug it into your calculator. Minus 780 minus 320 divided by minus 4 is 275 kilojoules per mole. So I'm just going to write over here, this is equal to 275 kilojoules per mole. That's the final answer for the SF bond, for a single SF bond. Over here, bond breaking is an endothermic change and bond forming is an exothermic change. You already know that. Bond energy is the amount of energy needed to break 1 mole of a specific bond. That is additional information. So over here, we need to find out the delta H value basically. So what is delta H? Is the total energy over here minus the total energy over here. So the way to go about this would be taking counting how many CH bonds there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, right? 3, 3, 2, 8. And the CH bond value is 412. So this is going to be 8 into 412 plus the CL-CL bond is 242. And from that, we subtract the HCl bond, which is over here 431, plus the bond over here, which is going to be 1, 2, 3, 4, 5, 6, 7, 7 CH bonds. Sorry, CH bonds is 412. So that is something you need to make sure that you don't mess up. So that is 412. The 412 plus the CCl bond, which is over here 338. Now see, one thing I forgot to add is this, the CC bond over here. And there are 2 of them on this side and 2 of them on this side. So you can add that, but if you think about it, they'll just cancel out. And that's the same thing for this also, the CH bonds over here. They are the same quantity, except this one has 1 extra. But I added that to make it simpler. So over here, I'm just going to add over here 2 into the CC bond, which is 348. So 2 into 348. And over here, same thing, plus 2 into 348. So just put this in a calculator and simplify this. 8 into 412 plus 242 plus 2 into 348. That is going to be 4,234. So I'm just going to write on top of here 4234 minus 431 plus 7 into 412 plus 338 plus 2 into 348, which is going to be 4349. And this, if you subtract them, is negative 115, which means that this is an exothermic reaction because delta H is negative. And that is basically it, right? One last question. Ammonia is used to make nitrogen trifluoride. Nitrogen trifluoride is essential to the electronics company. That's not necessary. Determine if the above reactions are exothermic or endothermic using the following bond energies band by completing that. Okay. So NH bonds, how many NH bonds are there? There are 3 NH bonds in the reactants and in the products as well. If you have that, which is 3. So NH is 390 into 3 of them. So that is something that's already done for us. The FF bond, there are 3 of them. So we just do FF is 155. So 155 into 3. It's going to be 155 into 3 is 465. The NF, there are 3 of them again, 1, 2, 3. So NF is going to be 280. So I'm just going to write 280 into 3 in my calculator, and that's going to give me 840. And the HF bond, there are 3 of them, and it's 565. So 3 into 565 is 1695. So what we need to do is find out delta H. And what is delta H going to be? Of the reactants minus the products. So the reactants is NH, 3NH, and 3FF. Is going to be 1170 plus 465 minus the triple F bond, which is going to be 840, plus HF, which is going to be 1695. And this is going to be what? 1170 plus 465. This is 1635 kilojoules per mole, or just kilojoules, minus 840 plus 1695, which is 2535. This is going to be minus 900 kilojoules per mole. So once you find that out, the reaction is exothermic because the delta H value is negative, and that is the simple answer. And well, that's it. Thank you for watching.